one part. Then safety also we discussed. Same, since the key functionality is, separate in different domain controllers, the safety workloads also is more, manageable in terms of getting the certification or making it safety compliant. It is more easy. But when it comes to SDV, it actually, I mean, consists of multiple domains itself, including the all the mixed criticality workloads. As I explained, the QM or ASIL, ABCD, any levels of it, and hypervisor all put together. So safety certification or taking safety compliance is more difficult than going for domain. Then another part is migration approach, right? So we cannot simply go from the distributed ECU environment into all of a sudden into one central compute architecture, because that is too much disruptive. Such a change. So usually it would be like the first we go into a domain for specific things, and then only I think the OEM will move to the central compute. And then the final part is supply chain. So the OEMs should get the materials, right? Including MCU, SoC, or all the materials. So domain means we have a better supply base. The SDV means or HPC means actually only few players are there who is actually giving the HPC level boards. So that way also, supply chain is also an important factor. So what is happening is OEMs are actually moving from domain plus zonal. That means it's not like they are completely moving, going from the distributed environment into zonal or central compute altogether. It's a mix. So they are making some of the ECUs as domain controllers. Also, they are making some of the ECUs as zonal controllers. And then finally, they will go to the central compute plus zonal part. So that is how and that again, not for all the models. It would be again only for the premium models. That is what would be the trend. Okay. Now, though, I explained things, maybe you would, I don't know how much you are interested, but still, this architecture kind of things would give you some more insight into what exactly we are talking about. So, as I said, the hardware platform we discussed, when you see standard compute, fundamentally it is kind of MCU. And high performance compute means where you will see the application kind of core, including the different accelerator kind of core, right? We have seen the DSP, the NPU, all sort of accelerator kind of cores, right? All put together is what we call the high performance compute. And then the simple MCU, or maybe you can also add DSP also there. That is what the standard compute. So the architecture would be like you would be having a kind of hypervisor, an example. Whatever we put here is just an example. So here I mentioned QNX and Green Hills. There are many other hypervisors available. So as an example, we put QNX and Green Hills. So there would be a hypervisor which would be actually, giving an abstract for the different type of OS. You can see here there's an real-time OS there and a POSIX OS there. So for both of these OS, since the hypervisor is there as an abstraction, for these both OS, it can actually see the hardware, whether it is standard compute or high performance compute. It can actually see it as a, I mean, exclusive access. So you don't have to worry that there is another OS which is also trying to access the same hardware which it is accessing, because the hypervisor will take care of that. Okay, so that will be there. And then on top of that, we will see different type of middleware services. It could be AutoSAR or over there, or the robotic operating system, ROS middleware. All this kind of middleware can be there, and it can be third-party services also, off-the-shelf components. Then on top of that, we will have the actual vehicle functions, whether it is vehicle software controls, VEC kind of things, or autonomous driving, or advanced driver system, or e-cockpit, or the EV, like BMS, inverter, all sort of um, applications, or connected. I mean, the vehicle is again connected, right? You will have telematics control unit or gateway, VTEX, all sort of functionalities would be there. So that is all you can see in the right side vehicle, right? That is actually which is sitting inside the vehicle. And you will also have a lot of functions working at the cloud. That is what we call customer experience or digital twins or touch points or ecosystem APIs and all, which would be, so there also you will have many applications which would be running. So initially it would be like, for example, prognostic kind of things. I mean, you would be actually trying to get all the data from the vehicle and then trying to generate different kind of insights. And from there we can actually make different type of data analysis, and then we can make sure that, I mean, we can easily diagnose the vehicle, or we can understand the customer profile and then offer service according. All sort of things will be there. Later, it is even possible that whatever, for example, AML part, right? So even though we are actually talking about very high compute device, still the volume and the power which is really required at the vehicle level, you cannot have everything within the vehicle. So many of these things later it can be actually done in the cloud itself. So that means some of the AML actual in-vehicle operations, whatever is required, can be executed in the cloud, and then the result is only what it would actually give back to the vehicle. So that way also it will happen. So that is at the end, that would be where the software defined vehicle will end up. But I mean, as we discussed already, I mean, for all these things, we need the HPC system. Okay. Now, I'm not going to explain it more. I just want to give you little more on what we discussed just above. On the left side, you can see that we will have the real-time OS and all. That is like if you have a real-time, hard real-time requirements where you want to perform some control operations, you can still put RTOS there and then you can achieve that. Then you will also see that there are different type of accelerators. OpenVX, TADL, PDK, all these are kind of things which is, for example, we are talking about TDF4, it is TAE. So the chip and the TA would actually give all this kind of, I mean, components or libraries which we can integrate. So on top, you will see the actual application, for example, ADAS application here. And then you can see an ARM trusted firmware. That is more from a security perspective. So you have to make sure that when your SoC is booting up, it is actually doing a safe boot. I mean, it is authentic, all sort of things, right? So fundamentally, they separate the domain itself. So that means you have special hardware by which, I mean, you can actually make sure that, I mean, the safety aspects are also met. Then on the right side, you can see, I mean, an application called like A72. There also, I mean, as an example, Linux is running on top of that, a container infrastructure where you can actually instantiate different containers. On top of that, you can have middleware. It could be adaptive AutoSAR or other kind of middleware. So this is kind of an architecture. I mean, this is again an example only. So this is how the architecture would look like. So when we say SDV means, so it is not just SPC. So all these kind of components and different combinations of this, OEM wants to keep it as one bundle, which has to be configurable, scalable. Scalable in the sense you should be able to use it in a, for example, in a zone controller that is not as complex as the central compute, right? So it should be, you should be able to configure the components so that only the necessary components would go to the zone. And at the same time, you should also be able to use the same software for the HPC part. So that means it is highly scalable and configurable, right? So that sort of things they have to develop. So it again includes elements from multiple parties. Some will come from the tier ones, some will come from the software vendors, some will be OEM owned. All these things will come. Okay. So moving to, I mean, I also kept some architectural considerations. I will just give a high level. What we are discussing here is, for example, when we go to the SOC part. So as you understand that SOC is heterogeneous, right? So typically it's called different islands. So we call it like a main domain island and MCU island. So MCU island is more from a safety perspective. Here the important factor is a firewall. So firewall means it is again like a hardware um, itself by which it actually enables specific access at the hardware level itself. So that means it can actually protect some of the peripherals, some of the memory regions, some of the cores, getting access from the other cores. So that way, we can actually configure this firewall so that we can make sure that we have a clear isolation between, I mean, safety domain and non-safety domain. So that is, I mean, those kind of features are offered in the SOC. And also in SOC also we can see that there will be a real-time cores. It's not just the application cores. So we can actually put some real-time or common loads also into the real-time cores. So that is also possible. Um, Again, just to give you another example, an SDV use case in ADAS. So I just explained to you an architecture earlier, but just to give you how it works, for example. So you can see down, I mean, the hardware virtualization is there, fine. And then on top of that, Linux is there. The Podman here, whatever we discussed is the container runtime, right? So if you, when you have the different containers or the application components, this is what it actually, I mean, instantiates or manages this software into the ECU. Then you have different features like object detection, the forward collision warning or lane departure warning, and the actual display inside the vehicle and camera. All these kind of applications are there. So what is happening is, for example, you can see in cloud, you will have a lot of database, lot of applications. So on top, assume that it's a mobile device and you have some app there. So from the app, you can actually, I mean, try to contact with the vehicle and then see that, I mean, what kind of user is actually, I mean, using the vehicle, right? So that you will get from the app itself. So the app will then actually understanding the user, it will actually communicate to the cloud. Then it will actually get a profile data for that specific user. Then with that profile data, the vehicle then again communicate to the cloud, and it will actually then try to understand what are the different preferences for the user, and then it can actually automatically take all those preferences and the required containers from the cloud and then instantiate in the vehicle. So and MQTT is it's an application protocol. It's a simple application protocol. It's like subscribe broker kind of things, and it's just to say that one protocol being used. And SDV orchestrator means fundamentally it actually orchestrates. So that means it understands the profiles, and based on the profiles, it actually see that again what kind of features would be required, and actually it can actually instantiate those kind of features, taking things from the cloud and then load it in the actual ECU. Okay, so I mean this I just put, I mean it's image from the NVIDIA itself, just to give you an overview that the big players like NVIDIA or other players, actually they are investing in the HPC part heavily. So whatever Orin you are seeing here, that is what they have been using till last year. And now they have introduced a new HPC, it is called Thor, and it also has a lot of accelerators. All these kind of accelerators are all focused on the AI part, AML model. So you are actually getting more and more, I mean, power, I mean, features and specific encoding, specific model and all, by which the idea is that, I mean, the the developers are actually getting all the features so that they can go for the, I mean, AML complete use. I mean, for example, if you look Tesla, right? So Tesla, they also have the software defined vehicle, but it's their ADAS system is only up to level 2. Um, then There are other players like from Google and all. They have up to level 4, not for the passenger vehicle, but for the robot taxi kind of things and all. Only for the taxi purpose, and again on the specific regions. The point here is Tesla is actually using only camera-based system. Okay. Whereas the others, for example, Mercedes-Benz, they have level 3 now. They are actually using camera plus radar plus lidar plus HD maps, all kind of things they are using, and that is how they are actually achieving the level 3 or level 4. Nobody has achieved level 5 yet. Now the point is Tesla is using only camera. It's not because they cannot use the other radar, lidar, and all, but they wanted to really go with camera alone. The advantage is that they are heavily depending on the AI part. So now they are behind, but assume that maybe in 2 3 years later, if they can really achieve the level 4 kind of, I mean, automation, then across globe, I mean, they can actually launch their vehicle because they are not at all depending on any radar or lidar or any other device, right? It's only, I mean, it's only a camera. It's almost like human. So they don't need any HD maps. They don't need have to understand what is already there. Nothing. It's all based on the camera based. So they don't have to worry about anything. They can simply put their vehicle in anywhere in the world. So that is what they are. But the point there is then they are heavily depending on the AML part. So they are heavily depending on the AML part. Therefore, this HPCs and how it is coming and all is actually going to play a big role in those kind of transformation. Now for Tesla, I mean, they are not going with Thor. They, I mean, till now they were actually using the Samsung SoCs. Now they are actually going to design their own SoC itself. So with, I think it's a 3 nanometer technology and all. So with that, I mean, they expect that their AML would be actually getting more, I mean, capacity performance. With that, they expect that they should be able to achieve whatever performance they are looking for. So the point what I want to highlight here is there is a heavy, I mean, investment or focus on bringing more and more, I mean, accelerators just to support AI part, AML part. So and that is where everybody is going after. Okay. Now just to, I mean, in NVIDIA terms itself, for example, what is more in Thor, you can see that just in GPU, CPU terms and all, GPU itself, I mean, the Orin is the earlier one and Thor is the new one. You can see that the Thorin, it's actually uh, uh, almost, let me see, yeah, I mean, you can see it is kind of 14 years scores, I mean, compared to the 12, what they originally had. Then the performance speed, the RAM access speed, now they have 273 GB, earlier it was 205. So it also supports 26262 SLD. And on top it is written, so it is almost like 7.5 times a compute than Orin. Um, and it has, I mean, 2074 teraflops, I mean, that much computing power. So all what I want to highlight is, I mean, the HPCs are becoming more and more compute capable. It's all purely looking at the AML capability. I mean, it wants to give more and more AML capability. Okay. So just to, I mean, since we are all from the academic background, I just thought, I mean, what could be the core skills which would be required in the HPC part or SDV part. So the embedded core essentially it remains same. I mean, it would be still required because you would still have some MCUs which is actually running in the different part. I mean the sensors or actuators where it is connected to the sound controllers. So definitely the C++, the MCU SoCs, RTOS all would be required. It will be even required in the even the HPC part as well. Then networking. So one of the item I didn't specifically says, say, when we talk about HPC or SDV, the backbone, network backbone will be fundamentally with Ethernet. That is also with gigabit. So gigabit Ethernet would be required with time synchronization or time sensitive network and all. So that is also an element. Then AUTOSAR is, I mean, kind of a standard established. I mean, people are also, I mean, looking for alternatives. So still, for the real-time issues, classic AUTOSAR would be still be there. And for the application core, or where we talked about the POSIX OS, adaptive is just an option. There are also other middlewares. Then if you look into modern software, I mean, we can see that latest C++ 1720 standards, then CI/CD integration, the configuration management systems like Git and different type of automation testing, all would be required. And I put Linux and virtualization, but essentially the QNX, the integrity and VxWorks, all this kind of OS is coming to the automotive. So, I mean, not coming, I mean, VxWorks is coming to automotive and others are already prominent in automotive. Then we need to understand the different type of distribution, the Octo, and then the containers approach, hypervisors, all sort of things. Then cloud and OTA part, for example, the software or the update or firmware of the update, and different type of vehicle APIs, the different type of protocols like MQTT, all these kind of things. Then AI, definitely. I mean, I know that this was linked more with AI. Definitely, AI is going to play a big role. There, we need to really understand. I mean, we understood that the essential blocks are GPU and NPU, right? From an AI perspective. So that is there. And then the derivatives of this is coming as different accelerators. So we need to understand how it works and what kind of models. I mean, there are different type of models, right? So what kind of models for what kind of applications. Then, since it is automotive, it's, I mean, passenger car or even the other commercial vehicles, safety and security will definitely play an essential role. Then the architecture, definitely the zonal computes, what were discussed, the subzone architecture and HPCs, all this could be kind of, I mean, core requirements. I mean, I can also say that I didn't put Python here. I mean, Python is also being used for the automation purpose, not really for the coding. I mean, automation purpose and all. Then earlier we have seen CUDA, OpenCL and all. Those kind of things all required. But I just put some of the essential skill required. So I think we are already, I mean, almost 7:25. Maybe we can spend another some time for, I mean, open discussions. Yeah. I mean, with this, I mean, deck is over. I hope I was able to give you an overview. Maybe we can discuss if you have some questions.
Dear participants, if you have any queries, please feel free to ask.
Thank you, Lina, for the nice session, and extremely sorry for the disturbance in between.
Okay, that's fine.
Uh, I have a question.
Please. Yeah.
Um, so when we look at this automotive domain,
Mm-hmm.
from an academic point of view,
Mm-hmm.
the problem is most of the solutions are proprietary in nature. So, from faculty or researcher point of view, if we are trying to do something, it is not that easy.
Mm-hmm.
So, can you suggest some area worth looking at for a fact for an independent research? You can think of it like that. Uh,
See, if you really want to learn the concepts, the architecture, and even the end-to-end philosophy, see, we have the Linux distribution, right? See, we have Linux. Then um, uh, most of the chip vendors, they are actually offering the low-level drivers. hmm, I mean, often free of charge. So we can actually, I mean, you have to decide definitely a kind of board for you, an SoC, which would actually have some MCUs and DSP and um, that is anywhere required, right? So because you really need that hardware part. But once that is there, I think from a software perspective, the entire firmware is, there is open source. So you can take the Linux open source, and then in the real-time world, you can actually take free RTOS, and then for the MCU and all, whether it is NXP or NSA, all of them are giving their driver for evaluation purpose. So that way, actually, we can build the entire stack, the entire components, and then that should be fine. So, my point is that there is open source community or open source components which is largely available to explore all these kind of areas, right? For example, there is an consortium called Sophie. So maybe I can share the link later. So they are actually again giving an architecture itself, which we can use for the SDV part.
Okay, thank you.
And was the topics relevant for your interest, or I just wanted to know that when we say HPC is only one item, right? So we cannot talk HPC without putting the relevant element along with that. I hope that way it was okay, right? The content, whatever we covered.
Yes, we have a mixed audience here.
Okay.
Any more questions from the participant side? Sir, I think no more questions from the participant side, sir.
Okay, then shall we
Thank
wind
you
up?
so much.
Yeah.
Yeah, thank you so much for the informative session, sir, and for accepting our request.
Yeah. Thank you. It was my pleasure. Okay. Thank you.
Thank you, sir.
Bye.
Dear participants, we will have a break for 10 minutes. And the next session will start at 7:40. Please use the odd link to join the next session.
Hi, good afternoon, everyone. So, my name is Vishwajit. I work in Jaguar Land Rover, UK, as a lead software engineer. So, in today's this session, I'll be giving an overview on artificial intelligence in embedded system with a focus on automotive domain. Okay, so before moving on to the details, I think it will be better to have an understanding on the direction in which the automotive industry is moving in. So OEMs globally now are moving towards software-defined vehicles, electrification, net zero emission, and AI-enabled features. So since I'm from JLR, so we'll just start with a video from JLR showing the future strategy for JLR. So let me.
Reimagine is our roadmap for the future. A sustainability-rich strategy that delivers our vision to be the proud creators of the most desirable, modern luxury brands for the most discerning of clients. It's about becoming carbon net zero by 2039. It's about our house of brands: Range Rover, Defender, Discovery, and Jaguar. truly differentiated global brand worlds that embrace our modernist design philosophy and are emotionally compelling and unique. Brands that will deliver our all-electric future. It's about enhancing our clients' experiences through pioneering technology and digital services, working with global startups and scale-ups to harness new thinking and opportunities. It's about partnering with innovators in their field, strategic collaborations that allow us to lead, not follow. Reimagine is underpinned by our internal refocus transformation, bringing positive change to every corner of our company. People are the soul of our business, the ones living the exceptional, creating proudly with purpose and in unity. Together, we are JLR.
Hi. Okay. Yeah. So then, what is embedded AI? So it's basically running the machine learning algorithm or the AI, artificial intelligence algorithms directly on an embedded target. So then, why is it required? Why do we need to run the machine learning algorithms in an embedded system, or like instead of running it on a cloud or somewhere where we can have a huge resources available for running the algorithms? So the first reason is actually the real-time performance. So especially in automotive system where safety is critical, so we might need faster results, which and reliable results, which we won't be able to ensure if we are running the algorithms in a cloud system and trying to retrieve the results from the cloud. Say, for example, in an advanced driver assisting system where it needs to detect an object and do an emergency braking, the latency that can be allowed may be 100 millisecond or something, which we may not be able to achieve without implementing the algorithms directly inside the vehicle. So then there are limitations like the resource constraints. So when we run the embedded algorithms inside, or the artificial intelligence algorithms inside an embedded system, the resources will be constrained. So there will be limited resources, limited power, limited memory. So it will be a balance between the feature and the computation power. Then the another aspects of embedded AI is safety. So when including AI in safety critical applications like automotive industry, automotive software, so we need to ensure that it follows. So there are regulations developed. It follows the proper process, and we need to ensure the results will be reliable, and it should be predictable and verifiable. Okay. Then, so another reason to the reason to move towards running everything locally instead of running it in a cloud is one we already discussed, latency. Another one is privacy. So there are some data that we won't want to save outside. We would have to save within the vehicle itself, like data concerning users' privacy, like maybe the biometric data of a user or things like that, which we would have to store locally to protect the privacy. Then the next one is reliability, that mm, the system needs to work even if there is a communication issue and the vehicle cannot contact the outside infrastructure. Okay, and the main area where this artificial intelligence is used currently in automotive industry is ADAS, or advanced driver assistance systems, where we are using the machine learning algorithms to implement various features like object detection, pedestrian detection, driver drowsiness detection, lane departure warnings, traffic sign recognitions, etc. So for that, we actually use in vehicle, we will have a set of sensors, including radars, lidars, cameras, etc. And this the data from this needs to be analyzed and processed using machine learning algorithms or pattern recognizing algorithms to detect various objects and various scenarios to make better decisions. Another area where AI has scope is the predictive maintenance. So this is where the AI algorithms residing inside a vehicle can actually monitor the data continuously and predict when there is an anomaly is detected, so that the user can actually, the client can actually save money by not allowing, first by saving time, then by realizing there is an issue going on, or there could be a probable issue going on with the vehicle by getting a notification or something in either the cluster or the remote app which the user can have in his phone. So that's another area where AI can have some can play a role to improve the customer experience. The next one is intelligent cockpit. So that is, so there are two main applications here. One is it's part of the advanced driver assistance systems, that is a driver monitoring system. So it's part of, the system will be monitoring the driver's facial movements, eye movements, the head movement directions, etc., to derive to detect if the things like driver drowsiness detection, etc. Then there is the other one is virtual assistant. So like so nowadays all the vehicles will have virtual assistants using natural language processing and LLMs. The user, the client customer can now directly speak into the vehicle and give instructions, which the software can process using the AI algorithms and identify the customer's command and do the action. Another area where AI will play a huge role is battery management systems. So globally, all OEMs are going doing electrification and going in to produce EVs in future, and it's going to be, I mean, in most of the countries it's going to be mandatory to produce only vehicles in the near future. So the main challenge of having an electric vehicle is battery management. So there should be a mechanism to predict the range. So the customers have to be aware that how much range is left. So we can use AI-driven algorithms to predict the range, then do the health monitoring like the state of charge and the SOC and state of health of a battery cell can be monitored continuously, and any anomalies can be detected using LND AI model. The another one is thermal management. The battery thermal state, the temperature can be continuously monitored and any anomalies can be detected, and this will avoid having any thermal incidents or incidents involving high temperature risks. Okay. Another area where AI is currently being used is improving the normal software development life cycle process. So in automotive industry, we still use the V model, which is an old software development life cycle model, where in the left side of the V model has the development phases and the right side has the validation phase. In left side, from top to bottom, it starts with the requirements specification and goes to the high level design, low level design and implementation, and corresponding for each stage, the right hand side contains the validation of the artifacts of each of these stages. Like the implementation, for the implementation, there will be unit testing. For the low level design, there will be integration testing. For the high level design, there will be system testing. And for the system, there will be acceptance testing. So each of these stages of software development lifecycle stages has its own improvement, scope for improvement using artificial intelligence. So if we go to each of these phases, the first one is requirements engineering. So here the main advantage that AI can play is going through the requirements and automatically detecting any ambiguity or inconsistencies in requirements, then classify the requirements automatically as functional or non-functional requirements, and identifying the safety critical requirements and marking them as a safety critical requirement and deriving the safety levels required. Like we have different safety levels A, B, C, and D. So safety critical levels of each of these requirements can be assigned by an AI algorithm and classify the requirements accordingly. Then another possibility in requirement stage is the traceability. So instead of having different tools and users having to map requirements to implementation and then to test case manually, automation using artificial intelligence can reduce the effort required to do the traceability between requirements, implementation, and test cases. Okay. So the next stage in the system development, software development, is the architecture design. So this is the stage where the architect will be deciding what are the resources required, like how much memory is required, which microcontroller to be used. So what will be the predicted size of the software. So how much, what will be the network, so the communication bandwidth, how much traffic will be there. So all this needs to be considered when defining the system. So having an AI model in this stage can actually help the architect to identify the hardware resources, or the maybe estimate how much the software size would be and how much memory the software is going to take, and probably identify the bottlenecks and predict the communication bandwidths that is required. So if you have all this prediction at this stage itself, uh, the system can be defined more efficiently instead of having to rework again. And so adding again, if we had to change the hardware uh, resource at later point, it will be a huge change and will cost a lot. So having an AI model to help that at this stage will reduce the cost considerably. So then next phase is the application design or high-level design. So for this high-level design and implementation for the application software, the automotive OEMs are generally using MATLAB and Simulink. So a typical a typical automotive application software will be using AutoSAR architecture. That's an architecture developed by a consortium of different OEMs and Tier 1 suppliers. So an AutoSAR architecture will, so the image here shows the AutoSAR architecture. So the base layer will be the microcontroller abstraction layer, which hides all the, which deals with all the interactions with the microcontroller and the hardware level interactions. So that is then hidden from the higher levels. Then we'll have a stack of various service layers called basic software. So this will again abstract different services from the higher level application software. So like, for example, communication. So that the application layer doesn't needs to know whether the communication is going through CAN, I2C, LIN, Ethernet, or whatever be the underlying physical layer. The application layer doesn't need to know, which will be abstracted from the actual hardware implementation. Then comes the application layer, which will be completely abstracted from the underlying hardware implementation, which will be only implementing the algorithm side of the software. And for this, we are generally using MATLAB. So MATLAB and Simulink. So traditionally, the requirements will be manually converted into a MATLAB model, and from that code will be generated. So with AI, now we can have features like can give prompts to generate model from an instruction instead of having to design it. And another area where we can have some improvement is the model optimization. Once the model is developed, the AI tools can help help improve the model or optimize the model. And in addition to the application layer, there might be some hardware abstraction layers which you have to write manually, which may not be part of the basic software stack, which will, since it's not part of the algorithm, which will have a repetitive codes. So which can have, which we can actually automate and reduce the manual effort required for the for hand coding the abstraction layers. Then another scope of AI in this layer is in case of maintaining the legacy softwares. So a trained model can actually understand the legacy code and can help the developer understand the implementation better. So the next stage in the development life cycle is once the application software is ready, it's the integration. So the AutoSAR standard uses XMLs for integration. So each of these XMLs has a lot of parameters defined in them. So creating them, maintaining them are really difficult. Say if a component, ARXML has an interface from component A to component B. There's a communication from component A to component B, and it's defined in the ARXML. If any of these parameters has a mismatch between component A and component B, it will throw an error during the integration stage. So it is a time-consuming process, and it's very difficult to identify the errors prior to the integration. So probably so a model trained on ARXML can be used to auto-generate the ARXML from the descriptions itself, from the software design itself, so that the manually introduced errors will be limited, and also it will be able to verify the mismatches between component designs in advance. So another stage where we have the maximum use of artificial intelligence and time saving is the verification and validation stage. So this is a huge process, and it takes a lot of time. You have to write the test cases for each of the development stages. So there should be feature requirements from the vehicle. I mean, test cases in the vehicle level, test cases in the L3 level, or the ECU microcontroller level, and then requirements on the unit level, and test cases on the unit level. So all these were developed manually till now. Now with the help of AI, we can actually generate these test cases. So well-defined requirements can be used to generate functional test cases directly, and also we can generate the test cases to cover edge case scenarios. And to improve coverage, these test cases which are not functional can also be easily generated using the AI features in various verification and validation tools. So even including MATLAB and Simulink now provides features to generate the test cases automatically. Okay. Yeah. So then, yeah. So in AI test generation, the advantage of AI is it will be very easy to generate test cases that has various irregular behaviors in it, and it will be easy for, say, in case of computer vision or ADAS related test cases, it will be easy to generate test cases that looks at the visual data and compares the results, which can be easily missed if you are doing it if you are doing it manually. Then another possibility of AI in test case generation is generating complex scenarios, which can be either difficult. Currently, the OEMs are depending on the standard data sets available for that, for example, for traffic data and all. But with AI, even we can generate new data sets from an available one and reduce the time of having to create a new scenario and record the data. Yeah, so this is same. So another use is using the digital twin. So a digital twin of a vehicle is a virtual vehicle itself running in a cloud cloud machine. So where we can have photorealistic 3D 3D simulation environments, which can be driven by the AI agents. Okay. Another one in verification and validation is the hardware and loop testing and the issue root cause analysis. So hardware in loop. So every ECU after development will go into different testing stages, including integration testing and system testing. The first stage of system testing will be done in a hardware in loop environment, where we will have a simulator, a physical simulator, which will simulate the various sensor inputs, or it will be like a plan model that can actually simulate the physical sensor behaviors. So the ECU will be connected in a hardware in loop setup 24/7, and will be running various tests in various automated test cases. So in case of a failure, the logs for this test will be really huge, and analyzing it will be time consuming. So with the advance in AI, so now it's easy to analyze the log, so that we can detect the anomalies directly from the logs. So if we get a summary like so we have a difference in pattern at this particular time in a particular log, it will be easy to analyze that and see if it has any issues or in that area, or and there will be, so since everything is now in continuous integration, so once the software is developed and committed into a repo, it will be then picked up by the CA pipeline and built, and it will be flashed onto an ECU connected to a hardware and loop rig, and the test cases will be automatically triggered to run. So now if a test fails, the AI can actually do some root cause analysis on itself by maybe flashing the software that was built from a previous commit and checking whether the issue was introduced in this commit or if it was introduced in a previous commit. So with AI algorithms itself, we would be able to map issues to particular commits in the repository. The last stage of even after deployment, there is a maintenance stage. So currently, when software is deployed, software will be recording the data internally. Then, with the help of, say, like a change in temperature, change in pressure, or any other unexpected scenarios that happens during during the life cycle of the software. So, with the help of AI, it is possible for the AI model to change the parameter live at runtime based on the data it learns while it's with the customer itself. And also, over-the-air updates are available now for most of the ECUs in a vehicle. So when so if there is some issues identified, or if there is a new feature that needs to be integrated, it can be easily pushed to a vehicle using over-the-air updates. So the main challenges in including AI is, first of all, cyber security. So having AI algorithms added into the embedded systems in an automotive area will create another additional attack surfaces for the attacker to exploit. So this would need much more safety critical implementations and new standards to be developed for safety in automotive area. So the next one is ethics. So this is the classic clash. An example is the classic clash scenarios. So like when there is going to be a clash in a collision scenario, what should be the decision that the software should make. So the another thing is hardware limits. So the algorithms might need a massive hardware computing power, but since the vehicle won't have so massive computing power, means it needs it will drain more power from the vehicle, so the range will be reduced. So it will be a trade-off between feature and the computing power that the vehicle can provide. Okay, then looking forward, the future of AI will be moving towards completely autonomous vehicles. So that can be, so that will need the artificial intelligence or machine learning algorithms running on in cloud, along with the embedded or artificial intelligence algorithms running inside the vehicle. So the vehicles needs to communicate with the infrastructure, external infrastructure, and vehicle needs to communicate with other vehicles that are on the road. So we currently already have a vehicle to everything or vehicle to X communication, V2X communication, which allows vehicles to talk to other vehicles and traffic control units. So going forward, so this is prediction in the AI demand in various domains. that's all for this session. Thanks. Thank you, everyone. Have any questions?
So, dear participants, if you have any queries, please feel free to ask now. Sir, I think no questions from the participant side, sir.
Okay.
Thank you so much. Thank you
you.
so much for accepting our request and for handling the session, sir. Thank you.
Thank you. It's a pleasure. Thank you. Thank you for having me.
Okay, sir. Thank you. So, dear participants, a gentle reminder. Tomorrow, the first session will begin at 2 p.m., followed by another session, and the adult test will be scheduled at 5 p.m. So, as you all know, a 70% test score is needed to get the adult certificate. So, be prepared for that. All other details will be shared in the WhatsApp group. Thank you.